So I want to spend a little bit of time today going over this joint work with Brent Nelson, who was the previous speaker, about something we're calling free Stein dimension and free Stein irregularity. And out of force of habit, I wrote Stein information, so never mind that. And you know, as is traditional in sort of semi-board, semi-slide talks, it's some people give pictures of previous speakers. And if you go on Brent's website, you find this old-fashioned picture of him. So this is my co-author. And also, just to get back at Brent, I tried to find another funny, similar looking picture to make fun of him. But if you Google image search for reverse image this image, Google thinks that the relevant thing is someone in a plaid shirt. So I wasn't able to find anything too silly to put up. All right. So I want to start, don't know why that's there, start talking about free Stein information. So what's the goal here? Broadly speaking, our Stein dimension work falls into the category of regularity problems in free probability, right? And so what's the goal in regularity, or for regularity problems, regularity theorems, regularity properties? It's to take information about some tuple of generators of a von Neumann algebra, x1 through xn. And so some free probabilistic information, things about their behavior under a state or some such, and use that to get information about the von Neumann algebra they generate. And the idea at a very rough, very philosophical level is that a nice distribution over here should lead to nice properties of the von Neumann algebra. Woo. I can saw. Should lead to nice properties. And you know, this is at this point very vague, but to give a couple examples, one thing, for example, is if you have this modified free entropy dimension, modified microstates free entropy dimension of your tuple of generators, and you know that it's strictly more than one, then that tells you a lot about the von Neumann algebra generated by these things. So Voiculescu showed, for example, that means there's no Cartan subalgebra. It means that the von Neumann algebra is non-gamma. And Gay showed that it also means it's in fact prime. And of course, there's an issue with the microstates approach, which is that in order to say anything about some random variables using microstates, you need to have microstates. And now, based on this MIP star equals RE result, for example, we know that that's not a free assumption, that there are sort of bad examples out there where the microstates approach to entropy will just catastrophically, will be able to tell us nothing interesting, and not for sort of any reasonable reason, but for the cheap reason that things just don't embed into R omega. And so there's another approach also started by Voiculescu to these whole entropy questions, these regularity questions, and that's the non-microstate side. And so one sample of a result in that line is if you have the free entropy, the non-microstates free entropy dimension being maximal, taking on its maximal value of n, then that tells you, for example, that there are no non-commutative rational relations witnessed in the von Neumann algebra. And that's a result of Mai, Speicher, and Yin from last year. And I suppose for completeness, I should go back up and add Voiculescu. Ooh, my handwriting is bad. And Gay. Okay. All right. And so there's been a lot of power of, you know, saying these probabilistic things about generators have results in terms of von Neumann algebras. And so the free Stein dimension is a thing we introduced that falls really broadly speaking into the same philosophy in the same camp. So how can this be defined? Well, the whole approach behind non-microstates free entropy is to try to, what nice distribution should mean for some generators is that they behave well under free differential calculus, loosely speaking. And so what do I mean by free differential calculus? Well, you have the free difference quotients, the current term coined by Voiculescu again, which are maps defined on polynomials in your set of generators, taking values in the tensor product of polynomials in your generators, which are defined by the following properties. First of all, that they should be linear. Second, they should satisfy the Leibniz rule, so they should be derivations. And third, that if you take the ith derivative of the jth variable, you get 0 unless I equals j, in which case you get 1 tensor 1. Okay. And so just a quick example of what this does to a monomial. Well, you should how this map behaves on a monomial is essentially it reads through the x's and looks for any occurrence of the x with a matching index and adds one term for each where that particular variables are replaced by a tensor sign. So taking the first derivative of x1, x2, x1 gives you 1 tensor x2, x1 plus x1, x2 tensor 1. Okay. And then from this, we can also define the free difference gradient, which is just the map where you take all the derivatives of a polynomial, and the Jacobian as well, which on a tuple of polynomials gives you a matrix whose jith entry is whose ijth entry is the jth derivative of the ith polynomial. Okay. And so why are these things worth looking at? Well, it turns out, so the first thing we can do is we can view these as unbounded operators on L2 of M, which are densely defined on the polynomials, and they take values in L2 of M tensor M, or in L2 of M tensor M to the n, or the matrices, depending on which one we're talking about. So the adjoints go in the other direction. And I should pause briefly here to say that this is a little bit sketchy if there are algebraic relations between my generators, right? Because then these are I can only define these necessarily to satisfy these conditions if I actually have an algebraically free set of generators. So that can be a problem. But in terms of defining the adjoints of the operators, you can get away with that even if there are relations in the algebra. And what's the approach you take? Well, you just say, for any, you view these free difference maps as merely relations rather than functions. And then whenever you have a tuple A comma B, which is, for example, in the relation delta I, then you'll define the adjoint of delta I on some vector C to be equal to Q if whenever you have a tuple that is related by the partial derivative, you find that the inner product of B against Q, B is in the, yeah. The inner product of B is against Q, so B should be thought of as the partial derivative of A, and then that should be equal to, okay, yeah, so that shouldn't be a Q, that should be a C. Got it backwards. Should be equal to the inner product of A against, where's my other letter, Q. Okay, and so that is simply the usual condition for defining an adjoint, except now for a relation instead of a function. And so that's just a nice thing we can do to define these even in the case we're not algebraically independent. Okay, so why do we care about these things? Well, it turns out, for example, if you look at the vector 1, which is the matrix, the n by n matrix whose entries are all 1 tensor 1, then Voiculescu's free Fisher information of the tuple X is defined to be equal to the L2 norm of the adjoint of the Jacobian applied to this matrix if it's in the domain, squares, L2, if it's in the domain of the adjoint, and infinity otherwise. And so having this particular matrix within the domain of the adjoint of the Jacobian buys you a lot of regularity and a lot of power. And this has a lot of consequences in terms of properties of the von Neumann algebra. So it's a nice property to have, but unfortunately, it's also a very difficult property to check. And it can be quite difficult to find out whether or not one is actually in this domain without some special assumptions or some amount of regularization of your variables that might destroy the information you're trying to find about the original von Neumann algebra. So this is often too much to ask for. And instead, what turns out to be a useful property to look at is what Brent and I have been calling the free Stein dimension. And so that quantity is defined as follows. The free Stein dimension is defined as sigma of x, and it is simply the dimension as an M tensor M op module of the domain of the gradient closure, which takes values between 0 and n. Okay, and some things are not obvious here. So it's not obvious to begin with that the closure of this domain is an M tensor M op module, and it takes a little bit of work to show that it actually has that property, but and a lot of just sort of algebraic shuffling in order to get there, but it turns out that it is the case. And it's also, one can show that if the one vector, if this diagonal one tensor one vector is in the domain of the Jacobian, then that implies, in fact, that an entire dense subset is within the domain of the complex Jacobian, which will turn into a dense subset being in the domain of this partial. And so that tells us again that if we have conjugate variables, if Fisher information is finite, then this will take on maximal value, but it gives us some sort of, some slightly weaker condition to look at. Because, for example, one being even just in the closure of the domain causes this to be maximal, but that doesn't necessarily mean that that one is in the domain itself. Okay, and so there's a little bit more that's and so why is this a nice property to talk about? Well, one very useful thing that it does for us is that it can be shown to be an algebra invariant of the algebra generated by the x's. So we can't get all the way to the von Neumann algebra invariant. That'd be a very nice thing to do, because amongst other things, it would resolve the free group vector problem. But we can show that it is an invariant under algebras. And this is something that in general is very hard to do on the non-microstate side. And so it's nice to be able to do that. And I'd like to spend a little bit of time sort of sketching how that argument goes. And so the trick is to relate the domain of this partial derivative, which very explicitly depends on the tuple of generators x, to something that depends only on the algebra and not on the tuple. And there it's useful to consider the following set of derivations. So let me write down the theorem that I'm trying to sketch the proof of. Sigma of x depends only on the algebra generated by x. Okay. So how do we do this? Well, the first is we consider the following set of derivations, which we've been calling, which I'm going to denote der sub 1 tensor 1, that blob is a tensor sign, of c of x. Okay, and what is this? This is the set of all maps D from the algebra generated by x into L2 of M tensor M op with the following two properties. First of all, they should be derivations. So they should be linear maps obeying the Leibniz rule. And second, we should have the fact they should have 1 tensor 1 in the domain of their adjoints when they are viewed as densely defined maps on the subalgebra of, densely defined maps sitting on the subspace of L2 of M. We want 1 tensor 1 to be in the domain of their adjoint. Okay, and so it's clear that this set of derivations does not depend on x, but only on the algebra. And there are some other nice things about it. So the first thing to notice is that it admits a right action by polynomials in x tensor polynomials in x, right? So given two polynomials in x, I can define acting on a derivation on the right by just taking the derivation and then doing this hash operation onto the tensor product of P and Q. And so what is hash? Well, remember the derivation takes on values in the tensor product. And so I simply mean multiply outwardly. And in fact, if you, okay. So this is a write action. It turns out that you can also, well, it's not clear that this preserves the fact that 1 tensor 1 is in the domain of the adjoint, but with a little bit of algebraic shuffling, you can show that it does. And if you look at, okay, let me not do that in front of you. With a little bit of algebraic shuffling, it's not too hard to check that 1 tensor 1 is in fact in the domain of the adjoint. And now the most useful thing is that this can be put in relation with the domain of partial x star. Right? And I've drawn this in the wrong direction. And so how is this done? Well, given a derivation here, I'm supposed to send it to something that is in the domain of the adjoint of the partial derivative. And so what space does that live in? That lives in L2 of m tensor m to the nth power. So I need to come up with n vectors in L2 of m tensor m. And the vector I'm going to pick, which turns out to work, is the Tomita operator J applied to D of the first generator through the nth generator. Okay. And so with a little bit more, so a few things that need to be checked here. For one, it's not clear that these things in the left are actually in the domain of the adjoint of partial like I claim they are. It's not, but that again can be established with a bit more algebraic shuffling. It turns out that this is injective. That's not too hard to see because of course the derivation is completely defined by its action on the generators, and I'm recording here exactly what it does to all the generators. It's not clear that this map is surjective, but one can explicitly construct an inverse by really roughly speaking, sending a tuple of vectors here to, and it's supposed to go to a derivation, so it will be the map that sends P to the sum of the ith derivative of P hashed onto the ith coordinate of C. And sorry, I'm missing a J, I think. And of course, this not quite true. One needs to be a little bit careful in the presence of algebraic relations, but it can be made to work. And so there's actually now we have a bijective map which preserves the action, which takes the action of polynomials in X on derivations to their corresponding action on the domain of partial of X star. And so now if we take a different tuple of generators for our algebra Y, then we can compose these, then we can take two of these maps together, right? So we can take phi X for one set of generator composed with phi Y inverse for a second set of generators. That gives us a map from the domain of the partial derivatives with respect to Y to the partial derivatives with respect to X, and then which is an CX module map. And then one can upgrade that to saying that it also gives a bijection of their closures as m tensor m op modules. And so by explicitly constructing this map, we find an isomorphism of m tensor m modules, which tells us that they have the same dimension. And therefore our sign dimension, which depended only on, which was given as the dimension of the closure of the domain of partial X star, is the same as the dimension of the domain of the closure of, or the closure of the domain of partial Y star. And so it really does only depend on the algebra and not on the actual generators. And that's sort of how this goes. And, you know, I guess I've run out of time, or nearly. So let me just say in closing that there's a lot more nice stuff that we can do with this. So we can relate this as giving our Stein dimension gives a lower bound for the non-microstates free entropy dimensions for both types. And we can compute it explicitly in several situations, including any abelian von Neumann algebra or any free product of abelian von Neumann algebras, and some more nice situations besides. And we also have some nice results about how it works when taking, for example, power series. It behaves as one would expect. Okay, so I see the clock is ticked to 5:20, so let me stop there and thank you for your attention.